But first, we're going to pass it off to Abraham Vinod, who is from the Mitsubishi Electric Research Team in Cambridge, Massachusetts. And it's going to talk about some really cool stuff about using CVXPY for convex sets. You should be able to share your slide.
Thank you. Thank you, Pat. Can you see the slides right now?
Yes, we can.
Awesome. Let me also turn on the monitor pointer. All right. Thank you so much, Parth, once again for inviting me to be part of this workshop. I'm really excited to be here. We have had a good line of talks so far. So good afternoon, everyone. I'm Abraham Vinod. Today, I'll be talking about pycvxset, a Python toolbox for manipulating and visualizing convex sets. Before I start, I want to thank Merle for supporting my efforts on this Python library. I've been developing pycvxset on and off since 2020 and released the first version last year, fall 2024. So what is pycvxset? pycvxset is a Python toolbox to handle convex and compact sets. Currently, we support polytopes, ellipsoids, and constraint zonotopes. You can define these sets, manipulate them using a variety of set operations like affine mapping, intersection, etc. And you can also visualize these sets in 2D and 3D. My goal with this toolbox is to lower the barrier for Python users to use sets for purposes like control and analysis. And I'll show a couple of examples where we use these sets to do autonomous precision landing and also motion planning for drones. Why use pycvxset? First of all, it's open source. We license it under AGPL version 3 and plus. It has minimal dependencies. I use CVXPY heavily to encode a variety of convex problems that I deal with while doing the sets. So thank you all for the hard work on that. Additionally, it's statically type checked and also has near 100% code coverage. The code documentation is available online as well. So let me get started on the different set representations. So as I said, pycvxset supports convex and compact polytopes. So these are set representations you might be familiar with, either the half-space representation where you have a collection of linear inequalities and equalities, or the equivalent form on the vertex space. So they are these commonly used forms. A slightly more esoteric form is this notion called zonotopes, which are a fine transformation of a typically high-dimensional cube to a lower dimension. And finally, constraint zonotopes are generalizations of these zonotopes where you intersect these high-dimensional cube and then take the affine transformation. So one thing to note is these two representations on the corners, they're actually equivalent. And what pycvxset allows you to is define either of these representations and do these set operations that we were talking about. So it also uses pycdtlib to do this facet vertex enumeration. It's high computational effort, and some of these complications become even further worse as you go to higher dimensionality. Additionally, pycvxset allows you to define constraint zonotopes from these half space and vertex representations, and you can also go back via approximations, which I'll get to in a minute when I talk about plotting them. Just to show you how these sets look and how we use in pycvxset. So these are like three sets I will define using this code. So on the left is the simple probability simplex, which can be defined like this. We can define an using pycvxset like this, where you give the half spaces and the linear equality constraints. pycvxset will give this output where it'll identify these hrep form, the half space representations. And whenever you trigger or ask for the vertices, it'll automatically do the conversion and give you the vertices back. Similarly, you can define the constraint zonotope from a polytope, and it will do this corresponding conversion and give you the constraint zonotope. And finally, if you give it a collection of vertices, it won't naturally trigger the half-space representation, but it'll retain it as a convex hull of points. And finally, if you have a zonotope, in this case, an axis-aligned rectangle, it'll automatically detect that as well. Simultaneously or parallelly, pycvxset also supports bounded ellipsoids, so you can define them either in the quadratic form or an affine transformation of a ball. So this also supports degenerate ellipsoids in the form of a low-dimensional ellipsoid as well. So this is how you would define an ellipsoid in this case, and pycvxset lets you interact with it and ask for its dimensionality, singleton, and things like that as well. So let me kind of quickly go over a few set of operations and talk more in detail in the applications, how they kind of play in. So pycvxset naturally allows you to do affine transformations like stretching, shifting, rotation, and things like that, projection of a point, checking if a given point or a collection of points are within or outside the set, computing the support function or support vector. These are like affine shifts of an affine half space that touches the set. And similarly, bunch of geometric operations like finding the maximum volume ball that inscribed in the set, maximum volume ellipsoid, minimum volume ellipsoid covering the set, and minimum volume rectangle as well. Additionally, some of the other set operations which are really crucial for control applications are things like orthogonal projection, that you can think of it like a shadow of the set to a lower dimension, intersection with a collection of linear inequalities, intersection with linear equalities, for example, in a affine set, in this case, or even asking like whether a set is contained in a different set. That can be further used to check even equalities. And two other operations like Minkowski sum and point difference, where Minkowski sum is asking the question, if I have a set X and a set Y, can I translate it around and what's the outer coverage? And the point difference is the kind of flip of it, or it actually is also known as erosion, where you're asking the question, what all are the set points to which if I add the set Y, I'll get back the original set X. So these are useful for doing a lot of quantifier operations like there exist and for all in control. And finally, to plot these sets, for href, I can actually use matplotlib and pycdlib to plot them. For ellipsoid and constraint zonotopes, I use the support functions. So naturally, if you recall from the convex optimization classes, any convex set can be approximated to an arbitrary accuracy as a polytope. So I can define these sets, direction vectors, and get these set half spaces. And if I naturally increase the number of direction vectors, I get more and more accurate set representations. pycvxset also lets you spread arbitrary number of points on an n-dimensional sphere using difference of convex programming. So this is what I use internally to do 3D plotting and polytopic approximations beyond 2D. So this is sort of a non-exhaustive literature that I've been using a lot. Naturally, the convex optimization textbook has been very helpful. Additionally, I want to call out there have been a lot of toolboxes as well, primarily in MATLAB. And for me, that was the main motivation, that I wanted to use these capabilities in Python. pycvxset started off with one of the commits of pytope by Huring. And we've been developing a lot more, adding a lot of functionalities like ellipsoids and constraint zonotopes, and also the testing as well. Some of the details of this toolbox is available in my conference paper at 2025. All right, so now let me get more into why should you care about this toolbox, and I give you some concrete applications. So one application I'll talk a bit in detail is this problem of autonomous precision landing. As you guys must have heard, landing on the moon has got very exciting research actively happening right now. There have been a lot of few attempts right now. Some of them are successful, some of them had failures. And naturally, you can imagine the challenges associated with this problem is hazardous terrain, the need to do pinpoint landing, the need to handle uncertainty in navigation and actuation, and also the ability to be able to divert. Like a lot of things happen on the fly, and you need to be able to react to this. So at the heart of this is an optimal control problem where you have hard state and input constraints, nonlinear dynamics, primarily because of the mass dynamics that depletes in a particular fashion, and we have to be robust to the uncertainty involved. So some of this work I'm going to show next has been under review in this archive paper, and what I'm going to show you is a two-stage approach where we use these sets to actually tackle this problem. So on the sets, we'll be considering as an offline and online stage, where on offline, I'll be defining this sort of sets called controllable sets, which are the set of all states from which we can reach the landing zone at the origin under the state and control constraints. So these are the set recursions, which is well known in the control literature. And it turns out to be these 8-dimensional sets. They are involved in position, velocity, mass, and cost to go. So this may remind you of dynamic programming, and that's exactly what it is, just seen from a set perspective. So I'm actually literally computing the set of all states from which I can reach the terminal goal under the constraints. And the cost to go lets me retain the notion of optimality. And actually turns out we can also show that despite the dynamics being nonlinear, under these for this particular structure that's there in the problem, these sets are actually convex, and we can use convex optimization to analyze this problem. And if you have uncertainty, then these sets then are replaced or augmented with Pontryagin difference operator, and that allows us to also guarantee robustness to navigation and actuation uncertainty. So once you get those sets online, instead of solving a full-blown optimal control problem along the trajectory, we have to now just solve a series of one-step optimal control problems. This again might be reminiscent of Bellman recursion, where we're solving, where we already have the cost to go function, so we have the value function. So we now only need to solve for a control action that takes us from where we are to the next set, and keep doing this until we reach the horizon. So the problem in this case, as you can see, it just involves dynamics and the series of sets that we computed. And this naturally allows us to accommodate all the state constraints and be robust to the uncertainty that we were after. Additionally, these sets also allow us to incorporate or be different to the decisions that we make. That is, in general, you can use these sets to land the location, as we said before. But if you have an alternate site that you wanted to land, you could use these sets to land there as well. And natural question to ask is, could we do better, or could we be robust to the possibility that this landing site may have some perception error, and we retain the ability to land to this site down the line? So the natural answer is, of course, you can procrastinate. That is, we, instead of lying into the next set, lie in the intersection of these sets. And that will allow us to do this as well. Naturally, we can also use these sets to ask the following question, like what all are the landing sites that I can reach given my current constraints? And these sets can allow you to answer those questions as well. Another application that I quickly wanted to show you is we can use this for motion planning. Like in the scenario where if you have a drone that has a few trajectory points that needs to tackle and reach back to the station, naturally, this is a convex problem for linear dynamics. But these sets can also let you tell or give you information on what are the admissible deviations from which you can retain these or go to these waypoints while satisfying all the constraints and meet them. These can, for example, help us in a downstream task of alternate sites that could be additionally tacked on to the responsibility of the drone. And these, again, can be computed by a variety of set operations that pycvxset supports. So yeah, I want to leave some time for questions and feedback. So this is my talk. I basically went over pycvxset, and just to highlight, the next few steps is we will be releasing the py release soon. It currently uses pip install -e. Sorry about that, but that's coming up soon. And the next thing also is to support bounded norm cones as well. Thank you, and I'm happy to take any questions if I have time.
We have time for maybe 2 questions. If anyone.
I saw there were some questions in chat as well. I couldn't read it, but I'm happy to address that.
One quick question: are you able to use the sets that you define here as constraint sets in CVXPY?
I'm sorry. Could you come again?
Are you allowed to use the sets that you're defining here and use that in a CVXPY problem? Can you use it to define constraint sets within CVXPY itself?
Yes. So all of the sets I have has a method called containment constraints that spits out CVXPY constraints that you can directly fit into any CVXPY problem that you care about. So it naturally sets up all the necessary auxiliary variables and things like that, and gives you back the constraints.
All right. I'm not seeing a second question. And in the interest of trying to get a little bit closer back to schedule, I'll say thank you so much, Abraham. This was a fantastic talk on a really interesting topic that I was super enthusiastic about. So we get another round of applause.
Thank you.